Hello again, welcome back. So we've talked a bit about normal form games, we've also talked about extensive form games, and now we're going to talk about one of the areas that's been very active in new development over the past few decades, and it has to do with repeated games. So repeated interactions and repeated games are probably one of the more interesting applications of game theory in understanding real behavior. And in particular, when we look at most types of interactions, they are often ones that happen over time and not just once. So, for instance, when we think about things like buyers and sellers, for instance, one firm supplying another firm, they'll be working with each other over time. If we think about the firms that you buy many things from, so if you go to restaurants or you go to a local store, you might be going to the same one over and over again. They might get to know you, and that can change the interaction. Political alliances, so how do politicians, legislators act? Do they ever make arrangements and compromises? Are they able to do that over time? When we think about people, just plain social interactions, do you do favors for friends? Do you expect them to reciprocate at some point in the future? Workers, so team production, things where people have to rely on other people to deliver or to help them out. So there's so many settings where we have repeated interactions, so it's fairly fundamental to understand. So I think one of the more important observations on this is that when we look at these kinds of situations, it basically changes the nature of interactions. And in particular, we'll see this even in settings with complete information. So let's have a look at that. And one thing that I think is important to note is that the idea of repetition and how that changes behavior is so ingrained in our cultures that we even have language for it. So things like quid pro quo, literally meaning what for what, or that there's some exchange of services or goods that are expected, not necessarily at the same time. Tit for tat is a very interesting one that actually emerged from looking at a series of experiments that were run by Axelrod and Rappaport, where they ran repeated prisoner's dilemma tournaments over time, and they found this strategy emerging where people would cooperate as long as the other person cooperated, but if they defected, then they would defect. And this sort of tit for tat strategy, where you do what the other person did to you in the last period, is a very powerful one, and we'll talk more about that a little bit later. Do ut des, the Latin "I give so that you may give," is often said along with giving a gift of some sort, so there's some idea of reciprocation. And so let's have a look at some of these. And in terms of fixing ideas, there's many applications that we'll have in mind. So collusion among firms, social norms of favor exchange, reciprocal altruism. There's interesting stories about World War I trenches where once it became clear that the armies were going to be there for a while and it was somewhat of a stalemate, there would be communications between the different sides to alert each other of pending attacks, so that there wasn't as much death as there might have been otherwise. But we'll have a look at some of how the strategies of this work out. So to get an idea of how this all works out, let's start with a very classic example, the prisoner's dilemma, which we analyzed before. So we have the prisoner's dilemma that we looked at earlier. And we see in this situation that we have a classic situation where defecting is a strictly dominant strategy. So if we think of the role players' payoffs, they get a higher payoff by defecting no matter what the other person is doing. So in a one-shot game, we're stuck with a strictly dominant strategy to defect. And in the infinitely repeated game, in terms of a preview of ideas, it's going to be possible to sustain cooperation. So the kind of strategy that we'll be looking at is something where you cooperate as long as the other player cooperates, and if the other player stops cooperating, then you stop cooperating. So that gives players an incentive to cooperate for a while. Okay, so to begin to analyze this, Let's start by first looking at just finitely repeating the prisoner's dilemma. So instead of looking at it indefinitely, let's start by just fixing a number of times. So let's say we play the prisoner's dilemma 25 times. And both players know that it will be played 25 times exactly. And each time it's played, you get to see what happened in the previous version, and then you play again. So you play once, you see exactly what both players did. Both players know they see this. They play again, and so forth. So could you sustain cooperation in a finitely repeated prisoner's dilemma? Well, let's have a peek. Okay, so let's use our backward induction reasoning to start. So we've got a finite tree now, 25 repetitions of the prisoner's dilemma. I'm not going to try and draw that one out for you because with 25 times the strategy space, it's going to become quite complicated. But we can look at the last period. So let's suppose that we've gone through 24 periods of play, regardless of what's happened. So some play has occurred over these 24 first periods. Now we get to the last period, and we ask, what should the players do? Well, in the last period, regardless of what's happened, regardless of the history of how we got there, there's still a strictly dominant strategy now, forgetting the past, for each player to defect, right? So I get, regardless of what the other player is going to do in this period as a function of what's happened before, it's strictly better for me to defect than to cooperate. So each player has an incentive to defect. So in the last period, there's a unique best response, regardless of what's happened, right? So it doesn't matter what's happened, we're going to have each player defect in the last period. Okay, so now then we can go through the reasoning. Now it's better to defect than cooperate, since cooperating or defecting, you're changing your thing, is not going to change what the other person does in the last period. They're going to defect no matter what. So you should defect in the last period, second to last period. Right? So basically you play as if it's the last period, and now we just take that reasoning backward. You can do the same thing for the third to last period, realizing that no matter what happens in the second to last period, people are going to defect, and in the last period they're going to defect, and so forth. So as we run that all the way back, what do we end up with? We end up with defect in every period is the unique subgame perfect equilibrium of this game, unique thing that we find by backward induction. In fact, it's the unique Nash equilibrium of this game. So in this setting, there's only one Nash equilibrium, which is to defect in every single period. And you can go through the same reasoning. If anything's a best response, it's going to have defection in the last period. And now, given that the other player has to be playing a strategy that's defected in the last period, I might as well defect in the second to last period, and so forth. So you can reason through and actually reason that here you don't even need backward induction or subgame perfection. All Nash equilibria of this game involve defecting for all periods. Okay. So a couple of things to say about this. Actually, when you put people in the lab and have them play repeated prisoner's dilemmas for 25 periods, you will find people defecting often in the last period. So indeed, things will unravel at the end. But you will see also people tend to cooperate for some number of periods at the beginning of the game. And so exactly how they tend to play as if the game is more indefinite or repeated until they get close to the end, and then things begin to unravel. Now, the more times you give people to play these and the more experienced they become, the quicker it unravels. But the play does not necessarily follow this Nash equilibrium prescription exactly. But in terms of understanding, let's try and understand what happens if the repetition continues. So it doesn't stop after 25 periods. So what happens if two players are going to interact indefinitely with no known end period? So will that change things? Let's have a look. But first, before we go into that, we're going to have to define exactly what we mean by indefinite repetition, how do we set these games up, and so forth. So let's look at some general definitions of repeated games.